Standard potential and free energy is related as follows in this equation, where you have delta G and then you have negative NF E naught. And what do these all represent? Well, the delta G is that change in free energy. The N represents the number of the electrons being transferred from one to another. And then the F is the Faraday's constant, and that's 96,485 coulomb per mole. And then there's a dot, which means there's a multiplication, and this E represents electron in units. And we have the E naught, which is the standard potential. This is in voltage, joules per coulomb, or also known as V voltage. Utilizing this equation, you can find the relationship between the change in free energy and the voltage. Also, we can say that we can find the relationship between the standard potential and the spontaneity. So here's an example problem that we can try by utilizing this equation. Here is chromium that is solid plus 3 silver, aqueous that's going into chromium 3 plus aqueous, and then silver 3 silver solid. And it already tells you the electron potential, the standard potential, and that's 1.54. It's asked for what is the delta G naught at 25 degrees Celsius, and this is at standard state. And is this thermodynamically favored reaction? And then you will calculate the equilibrium constant, and that would be K. Let's dive into one question at a time. So let's look for delta G. Delta G is based on the equation. You can see on the top, delta G is equal to negative NFE. So we're going to plug those values in. So let me rewrite the equation here. Delta G naught is equal to negative NFE naught. And, well, we have to find out how much electron has been transferred from chromium to chromium 3, and then from silver to 3 silver. Okay, so what did we do? We put them in a separate reaction, in a half reaction. We have our chromium, and that's forming into Cr3 plus aqueous. And so this is an oxidation reaction. Let's look at the oxidation number for these. The chromium is 0. Chromium 3 plus is 3 plus. That means we needed to add 3 electrons on the right side of the equation to show that 3 electron has been taken out. Let's check for silver, okay? So silver, Ag plus, and then it's reducing to 3 silver, okay? So there's 3, this is plus 1, and there is 0 over here for its oxidation number. And then you needed to add 3 electrons plus 3 electrons to get to neutrality. Not 1, that's because it has 3 silver. So that means there's 3 positives to get to the 0. And so therefore you need 3 negatives, which is the 3 electrons. Having this 3 and 3 over here lets us know that we're dealing with 3 electrons movement to solve for the free energy. So we're going to write minus 3 electrons. Faraday constant, it's already given to you, which is 96485 coulomb per mole electron. And then we have our voltage, which is 1.54. 1.54. Now I can put V as our voltage, but I'm going to put it as joules per coulomb because that's another one. And it'll show you how everything kind of cancels out really neatly. So let me show you how it cancels out. I'm going to erase this so that it's not confusing. So let me cancel electrons. So that's on top, right? Coulomb, that's on top. So you're left with joules and moles. And that's good because that's what That's what delta G needs in order to become, to show that there is enough energy per mole to show the spontaneity. All right, so let's calculate this out on a calculator. We have our -3 times the 96485 times 1.54, and that gives me -445760.7. So that's approximately, I'm going to say that it's so we get -445760, -445760, approximately joules per mole. Now we can put this in kilojoules, and if you do put it in kilojoules, it will be 445 approximately 0.8 negative kilojoules per mole. Okay, so either way would work. I'm just putting a rough estimate in here. I'm not putting all of the values, nor am I putting in any in particular sig figs. So if you're wondering, what's the sig figs here? Probably 3, because we're dealing with 3 values of the voltage and everything else is an infinite mini. So let's go ahead and rewrite this in the correct sig figs. And so for the first one, it would be -4.46 times 10 to the 5 joules per mole. Or you could write this as -446 kilojoules per mole. So either would work. Okay, so now that I know what delta G value is this a thermodynamically favored reaction? Okay, it's a negative value, so that means yes, it is favored. So yes, favored. Then it asks for, there we go. Then it asks for calculate the equilibrium constant. So if you want to know what equilibrium constant is, it's that K. And remember, if you recall from a while ago, K is equal to the product over reactant and it's got exponent. You needed like an exponent X and a Y over here. So for here, the product will be chromium and silver, and solid is not included. It would be just Cr3 plus, and then the reactant would be silver plus. But here it's not asking for what is it individually, but it's asking for K. And the equation for this you need is delta G naught is equal to -RT ln of K. This is a while back equation where there's a relationship between the delta G, or the free energy, and with the equilibrium constant is this particular equation. Well, we know all of these values except for K, which is what we're looking for. So we're going to go ahead and divide this by -RT, both sides. And I'm going to go ahead and cancel this out. And we're left with ln of K is equal to delta G naught all over -RT. So delta G naught is -44760. Now, why am I using this giant number, not the sig fig one? It's just to get more of the accurate value. Joules per mole. And then on the below, R represents the gas constant. That's 8.314, and that's joules per mole dot K. And what is T? Well, T represents temperature. Temperature here, it's in Celsius, but if you were to calculate this out in Kelvin, you would get 298.15. And so I'm going to go ahead and, Kelvin. And so I'm going to go ahead and put this in here, which is 298.15 Kelvin. And what is that equal to? Then you punch this into the calculator. So let's go ahead and do that. So the calculation here shows what I had previously, negative 445760.7. That was my delta G I divided by the gas constant there, and then multiply that by the temperature, okay? And now, might not see the temperature. I'm going to move on to the side, but there is a 298.15. And after I have closed the parentheses, I get 180, about 180. And that would be my 180. I'm going to write it here now. So that's 180. And all of these guys, these units will cancel out. Well, the 180 is equal to not K, but ln of K. So how do I get rid of that ln? Well, you need to take it with the E. Okay, with the power of E. So meaning that E goes on the bottom and then the power of 180. Where is that in the calculator? Right here, you can see on... right here, you see that e's of x, that's second ln. So you're going to put second ln and type in 180. And then you should get the value you want. Or you could do e's of the second answer, which is the answer before. So this is about 1.49. So K is equal to 1.49. This is your equilibrium constant, okay? And not 180. 180 is the ln of K, but you want to get rid of that ln, and to get rid of that ln, you want to put with 180 with the power of E, and so therefore K is equal to 1.49. And then I think I forgot one more thing, times 10 to the 78. That would be important. And let me cross this out again. 10 to the times 10 to the 78. Okay. I forgot to put this 10 to the 78, and that's really important, which really shows that this equilibrium having constant having a really large value lets me know that it drives the reaction. It goes into pretty much into completion. Now that we have done some example regarding the standard potential and free energy, I want to kind of categorize everything together so that we can see the clear relationship between the standard potential, the free energy, and K, which is the equilibrium constant. So in the scenario before, we had the E value that was positive, okay? It was positive. Well, having the E value as positive, what did that mean for E naught? It meant that E naught would be negative, right? A positive here. And so delta G naught, okay, since this is positive and this is negative, that means that delta G will be negative. So delta G here will be negative. Whereas delta E was positive. Having delta G as negative, is it spontaneous or non-spontaneous? This is spontaneous. That means having E naught as positive, that means that it's going to be a spontaneous reaction. What do we know about K? Well, in the example before, we had a really large K value. In fact, it's going to be anything greater than 1. So it will be higher than 1, higher than 1. And many times it will be a very big value. meaning that the concentration of these product over reactant, the product, there will be a really large product. Well, what does that mean for if the E naught is negative? If the standard potential is negative, that means that delta G is going to be positive. If delta G is positive, that means this is non-spontaneous reaction. And having that standard potential being negative shows that it is a non-spontaneous reaction or process. What does that mean for K? That means you're going to have a very low value of K, or it will be less than 1. So the K will be higher than 1. This one, K, will be less than 1. And most likely it'll be a small value, meaning it doesn't really want to go into completion. They want to stay as reactant. So what about if the standard potential is 0? Well, that means delta G is, these are all standard, is also 0. And what does that mean for K? Well, it means that it's going to be at 1, meaning the number of the product and the number of the reactant will equal each other out.